Let's talk about multi-level gate circuits. Those of you who are in my class, this is the beginning of chapter 7. So let's start with the first circuit, the first example. A plus B. Obviously, this is only one level. There's only one operation. And here's what it looks like. Very simple. Now for the second circuit, A times B plus B times C. This circuit is two level. Now there's a very easy way to figure this out. First, let's write down the circuit AB plus B times C. Now, you see A times B, this is one term, so let's connect it into one circuit, one gate. B times C is another gate. And these two gates connect into another gate. So, it's not the circuit itself, but it's just a very quick way to figure out how many levels the circuit has. So you can see the top level, there's one level, here's a level, and below here there's an outer level. So top level is called level 1, so this should be level 2. Now this is called an AND OR circuit. AND is the inner level, A times B, and OR is the outer level. Now for the third example, this looks a little bit more complicated, but it's actually really simple. Let's use the same method to determine the circuit. A plus B times C plus D prime plus A times B times C. Now let's go for the innermost level first. This is C plus D prime. That should be one gate. And then A times B outside. It shows one gate. And that also includes the previous gate. And then A times B times C is a separate gate, which is also connected to another gate. So this circuit has 3 levels. This is the first level. This is the second level. And this is the third level. Now, can you tell me what level, what the levels are? Let's say the inner level, C plus D. So this should be an OR. Now the outer level is N, A times B, A times B times C. So this is an N. And the third level is an OR. So this gate, this circuit is called an OR and OR circuit. So a NOR gate is basically just a normal OR gate followed by an inverter. So here we have A plus B prime, and the circuit should look like this: A, B, followed by the OR gate, and then an inverter. It's pretty simple. Now, here's a 2-level NOR gate. It's basically just mean that there are 2 NOR gates inside. There's one NOR gate, followed by an outer NOR gate. So the first NOR gate should be A plus B prime. So here's the first NOR gate. Now here's the second NOR gate, C plus D prime. Oh, banana. And followed by the outer NOR gate. It's pretty simple. It might take a few tries to identify this, but it should be really easy afterwards. A NAND gate is very similar, so it's just an AND gate with an inverter. Let's make it quick. A times B, right? It's just a normal NAND gate with an inverter. That's it. And a two-level NAND gate is also the same, but with three NAND gates. Two NAND gates inside. Here's one NAND gate, AB prime. Second NAND gate is CD prime, and then an outer NAND gate. So the first NAND gate is A, B, and NAND gate inverter. Second NAND gate, C times D. And outer NAND gate. That's it. See? Now here's an activity that you have to do a lot throughout this chapter. It's converting another gate to NAND and NOR gates. Here's the first example. We have an AND circuit, A times B, and we need to convert it to a NOR gate. First and foremost, we need to recall that F double prime is the same equal to F. Now we need to apply this rule to our circuit. So what's the F double prime of AB is basically just A times B prime and then another prime. Now realize that inside here we have A times B prime. We can apply the Morgan law to the inside. So if we do that, we get A prime plus B prime and prime outside. This is a NOR gate. So basically we just convert an AND gate into a NOR gate. First, by applying the F double prime is equal to F rule, and then applying the Morgan law rule inside. So let me rewrite this to make it easier to see. So this is the Morgan law. Oh, come on. And let's draw this circuit. Let's see. So let's draw A times B first. A times B is a normal AND circuit, and A prime plus B prime and prime is a NOR circuit. So A prime, B prime, NOR circuit with an inverter. This would be the NOR circuit. Now we can apply the same steps when converting an OR gate to a NAND gate. So first, we apply the F double prime rule. F prime prime is equal to A plus B prime prime. And then we apply De Morgan's rule. So that would make it A prime times B prime prime. This is a NAND gate. Oh, let me see. This is your NAND gate. Now I don't think I need to draw this. But you see, it's pretty simple, right? Converting from AND to NOR, or from OR to NAND, we only need to apply the F double prime rule and then De Morgan law, the inside. Now we just went through converting from an AND gate to a NOR gate and an OR gate to a NAND gate. Now we are going to do the same thing, but with two level circuits. So let's say we have an AND OR circuit. F equals to A times B plus B times C. This is a two level circuit that we need to turn into a NAND circuit. So how would we do that? Of course, the first step is to use the FF prime. Right? So F double prime, F prime of prime, first be equal to everything here. Right? Now, what happens when you apply the Morgan law to the inside of this expression? We would get a NAND circuit. So bear with me. So parentheses outside and inside we have, remember, keep the terms as is. Don't apply the Morgan law inside of them just yet. So only apply the Morgan law to the outside expression. So this case will be A times B, everything prime. The plus becomes a multiply. So time B times C prime. And everything prime. So you see this is a NAND gate because this is NAND gate, this is a NAND gate, and they both multiply each other, and therefore the outside is a NAND gate. Here. Let me draw the two circuits. So the first circuit looks like this. A times B. So we have more of the NAND gate. And then C times B times C. Another NAND gate. And then they both connect to the OR gate. Right? And the second circuit, a NAND circuit, looks like this. Oops. We go back here. A, B. Those two G, a NAND circuit. And BC does the same thing. BC, NAND circuit. Everything goes to the NAND circuit. Everything goes to the NAND circuit. Right. Now, what if you want an OR NAND circuit? That we do then. Now, take a note. only when we start at the AND OR gate. Usually this is where you start with, because this is a min-term expansion. So you would use the double prime, F double prime first, and then De Morgan law to get NAND circuits. But after that, to get to the OR NAND circuit, you only need to apply De Morgan law again on the inside. Okay? So you see inside here we have the NAND gate. We can apply De Morgan law there to get an OR NAND gate. So let's try it. So let's bring it down. Right? Now let me write it step by step. So this A times B prime is a NAND gate, right? So if we apply the Morgan law to it, we get A prime plus B prime, right? And this multiplied in ways because we're not applying the Morgan law to the outside, we only apply the Morgan law to the inside, to each term. So B times C prime becomes B prime plus C prime. This is an OR NAND. You see, inside there's an OR gate, right? A prime plus B prime. This is an OR gate. There's no prime outside. And B prime plus C prime is an OR gate. And on the outside we have a NAND gate. This looks like this. Okay, so here's the circuit. A prime plus B prime. And this is, sorry about that. This is an OR gate. And then B prime, C prime. This is also an OR gate. And we take the next to a NAND gate. Right? And how do we get to a NOR OR gate? Let's move this bit. Notice that we still have a prime outside, right? So what happens if we apply the De Morgan law to the outside of the expression? Let's apply it. So if we apply the Morgan law, the outside prime goes away, right? And, oh, hold on, you're going too fast. So this is a term, right? An entire term, A prime plus B prime. So we have, when we apply the Morgan law, we prime it, and they're multiplying each other. So we change that to a plus sign, right? The same thing here, we apply the prime sign here and erase the outer prime. So if we apply the Morgan law to this expression, we get this, which is an OR NOR circuit. You see, inside there's a NOR. This is a NOR, right? A prime plus B prime. This is a NOR gate. B prime plus C prime outside is a prime, so this is a NOR gate. And everything is an OR gate. So here's the circuit. A prime, B prime. This is a NOR gate. And B prime, C prime. This is a NOR gate. Everything is an OR gate. Okay, so this is the circuit. Now let me recap. First, when you're given an AND OR circuit, and we'll double prime it, and then apply the Morgan law to the inside, you get a NAND circuit. And then if you apply the Morgan law to each term inside the NAND circuit, you get an OR NAND circuit. And then if you apply the Morgan law to the outside, you get a NOR OR circuit. Now, how do you get from a NOR OR circuit back to an AND OR circuit? Well, it's simple. You only need to apply De Morgan law again to the terms inside here. You see, this is a NOR circuit, right? A NOR gate, right? A prime plus B prime prime. So you apply De Morgan law to there. What do you get? You would get this term becomes what? You apply De Morgan law, it becomes A times B, right? And this term becomes B times C. You see, we're back to AND OR circuit again. So basically, just double prime it and apply De Morgan law until you reach the circuit that you want. Alright, so we just learned how to convert a two-level AND OR circuit to a NAND circuit and other circuits, right? So now what if you start with an OR AND circuit? An OR AND circuit is in a product of some form. So you get this by finding a max term expansion. Okay? We will do some examples later. So let's say we start with an OR AND circuit. A plus B times C plus D. This is an OR AND circuit, right? This is an OR gate, and the outside is an AND gate. I'm not going to draw the circuits out. So how would you turn an OR AND circuit into a NOR circuit? Well, you would apply the same step we did earlier. So first, we turn it into a double prime, F double prime. Right, is equal to this everything at double prime. It might look a little bit complicated, but stick with me. So basically, just apply two parentheses outside and two primes, right? And then you apply De Morgan law on the inside. Okay? So let's go one step at a time. So we're trying to turn it into a NOR circuit. So, and when we apply De Morgan law on the inside, the outer prime goes away, right? And A plus B, this becomes a prime, right? And they're multiplying each other, so we change that to a plus. Remember, De Morgan's law, okay? You gotta go double check that again if you don't know what it is. And this is a NOR circuit, you see? Because inside we have this is a NOR gate. This is a NOR gate, and in the outside we have a NOR gate. Now, how do we turn this NOR circuit into an AND NOR circuit? We just need to apply De Morgan law on the inside. See, each term on the inside is prime, right? This is a NOR. So all you need to do is apply De Morgan law here, and you get A prime times B prime, right? The same thing here, we get C prime times D prime. See, this is an AND NOR circuit because this is an AND gate. This is an AND gate, and the outside we have a NOR gate, okay? And then to get a NAND AND gate, we apply De Morgan law on the outside. So if we apply Morgan law, the outer prime goes away, right? Hold on, let's rewrite everything. So the outer prime goes away. The first term becomes A plus B. Wait. Nope, my bad. Okay, so we apply De Morgan law here. I went up one step too far there. So let's erase the other prime because we're applying De Morgan's law. The first term, we prime it, and this plus becomes a multiply, right? And the second term become prime. So this is a NAND AND gate. You see, this is a NAND gate, this is a NAND gate, and the outside is an AND gate. Okay. So how would you go from a NAND AND gate back to an OR AND gate? Simple. Just apply De Morgan law to each of these terms, and you should get an OR AND gate. Let's start with a simple problem. Okay. Using AND and OR gates to find a minimum circuit. to realize this function. Now, before I start the problem, I would like to clarify a few things. When the problem asks for an AND and OR gate, it really means that you can use either gates. And so you can make like an AND OR gate, on OR AND gate, on OR gate, or an AND gate. You see, so this problem gives you a lot of freedom. Now, if they were to ask you an AND, specifically AND OR gate, or an AND and OR gate, you have to set that, you have to specifically use that circuit. Okay, you cannot use if they ask you for an AND OR circuit, you cannot write an OR AND circuit as the answer. Okay, in this case, you can use either. So we're gonna use an AND OR circuit to make it easy. First, we have to let's make the K-map. So here's the template K-map. Let's start filling in the dots. So M4, here's 4, and 6, 7, 8, 9, and 10. So let's start finding the min-term expansion. This one, and here, and these two, this one. Alright. So this gate would be C, let's see, with the A prime B, and D prime. So this would be A prime B again, and C, right? This one is A B prime, C prime, and this one is A B prime and C prime. Alright, so let's write the new bit state. Let's see, double check it. Oh, it's actually lowercase. My bad. A prime B, B prime. So that's A prime B C. That's A B prime C prime. That's A B prime D prime. Okay. Now this is a two-level circuit, right? So two-level logic, right? The function is two-level. So A is only asking you to make a minimum circuit for this two-level function. Okay, so let's start making the circuit. It's really simple. Sorry, my tablet freaked out for a moment there. Let's redraw the circuit. So okay, and A prime B C, and A prime, and then A B prime C prime, and A B prime D prime. All of them are in the SOP form, sum of products, right? So, wait, sorry. yeah, some products. So this would be the inside of the NAND gates. It's all of the NAND gates. And then the outside would be an OR gate. There you go. That is the two-level logic circuit. Okay? That's just A though. So how would we make this into a three-level logic? It's pretty simple. All we need to do is to factor this. Okay? So right now we have a two-level circuit. So we only need to factor it to get through a three-level circuit. So let's see, we can factor A prime, right? We factor A prime, we get B times D prime plus B times C. And then, wait, no, we can factor something else. My bad. We can factor A prime B. And we can, if we factor A prime B, we get C plus D prime. Now this by itself is already a three-level circuit, okay? But let's see if we can factor anything else. Let's see. If we factor AB prime, because if you don't factor out everything, we cannot reach the minimum 12 gates, okay? So we need to factor as much as we can. So we factor AB prime, we get C prime plus D prime. Alright, so this should be enough. And if we draw a circuit from this function, we should get a three-level circuit. Okay. Let me get some space. Okay. Let's draw this. See the starting inside plus C plus D prime. C plus D prime. So that's an OR gate. And on the outside, we get A prime B. So it is an AND gate. There you go. And on the other side, we have C prime with D prime. In an OR gate. On the outside, we have A B prime. In an AND gate. So outside is an AND gate. And the outermost gate is an OR gate. So let's count the input. See, we have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 gates. That's right. So that satisfies the requirements. This should be the answer for 7.1. This is B. This is A.